the department Geosystems at Geosat has a lot of sections that look at different aspects of the system Earth in a systemic way, and it's a bit separate from the more disciplinary departments in that it has this systemic approach. But if you look at the titles of the section names, you can imagine quite easily that heat flow is of key importance to most of these sections. So if we think of heat flow as being embedded in a plate tectonic setting, knowing the geothermal fingerprint of each of these settings is of course key. And heat flow is a key thing to measure, to learn about it. It is important for geoenergy, for example, if we look for geothermal energy resources, or for geodynamics, if we think about deformation, and deformation can in turn be relevant for geoenergy if we want to avoid induced seismicity, for example. So heat flow is something important in both. So knowing this geothermal fingerprint is something that will help us. For example, if we look at different settings, you see here models that we did in agreement with those heat flow values that we had and those measured temperatures that were available and those geological data that was available at the time. You can see that the depth to the 100-degree isotherm can be quite different in different tectonic settings. You see on the upper left, the upper Rheingraben, once below topography and once below sea level. You see a young passive margin and an older passive margin, West Africa, Whirring in Norway. You see the Alps below sea level and below topography. And it's always the depth to the 100-degree isotherm. And you can see the difference can be kilometers. So if you go for the geothermal sweet spot, it's important to understand it. Central European Basin System, we are sitting about here. Is different again. So another magic number in heat flow and temperature adapt is the 450-degree isotherm that is generally taken as a proxy for the brittle ductile transition. It roughly corresponds to the one of quartz, and the quartz-rich rocks in the crust would then correspond to that. We learn increasingly that this may be challenged in the future, the more experiments we have. But it shows, if we compare it with the depth of seismicity that we observe, that it also correlates with the mechanical thickness of the crust, and it appears to limit the depth of the seismicity. That in turn means it also controls crustal strength, and that brings us to my other big topic that was in my title, the geodynamics. So knowing the depth of this isotherm is important to understand which part of the crust is seismic or not. And you can see, if we look now at the rift setting in the upper Rheingraben, it's quite a different pattern than the 100-degree isotherm depth, without diving too deep in the absolute values. And you can see that the two margins, old or young, may look very different at depth than they look in the shallow part. Before they were more similar, but now we see the ocean is hotter in the younger margin, whereas it is colder in the older margin. So understanding geodynamics will help us to, understanding the thermal field will help us to understand geodynamics. So what we see as well is, if we look at models of the crustal strength across the Alpine Himalayan zone, you see here is Tibet, Zagros, Alps, and so on. We can see in reddish colors weaker areas, and in lighter colors stronger areas. And we see that all the origins are weaker than their surrounding continental interiors. And if we plot all these strength values against crustal thickness, we see that the strength would increase infinitely if we would not consider crustal heat production. But if we consider crustal heat, radioactive heat production, we reach a critical value when the crust thickens to a certain point and then it becomes weaker again. And this is what you see here. So this is controlling the heat production is controlling the stability of the continental lithosphere. So knowing that is, of course, then relevant to understand geodynamics and deformation. Now, my last two slides show a heat flow, surface heat flow map. Brings me back to where we are here today. So this is a predicted surface heat flow of the North German Basin, Central European Basin System. This is really a very sensitive instrument. And we are sitting here now. And you can see the average color is green, which is typically 60 milliwatts for a continental interior of a stable interior of a continent. But you see also there are small spots that are much higher values. They can reach up to 120 milliwatts, which are salt structures. And if we take a cross section now through this system, and this is what I did here, from the North Sea across the entire basin system, and this is the geology you can see here. You see all these little spikies here, these are the salt structures, this is the crustal structure, here is the moho. And if we calculate now, what is the heat flow at the surface, at the base of the sediments and at the moho, and we see so many different levels. So this is at the surface, this is the average 60 milliwatts, this is at the top crystalline basement, and this is at the moho. And you can see the surface heat flow is a composite signal. It can be half crust, half sediments, half mantle. It can be mostly crust, depending on what your geological structure is. And that brings me to my outlook part in my 5 minutes presentation. We need to take also care about geology and integrate it increasingly with the heat flow that we will have soon. And that was also my comment about the international database. But for all of this, we need excellent and fair heat flow data. Thanks again to the team, and thanks to you.